Janisa, అంటే జెనిసా ఫస్ట్ సెషన్ కంప్లీట్ అయిందంటే సెకండ్ సెషన్ తీసుకుంటున్నాను. సెకండ్ లింక్ పంపించాను కదా, దాన్ని యూజ్ చేసి జెనిసా అని క్లాస్ అటెండ్ అవ్వమని చెప్తున్నాను. లింక్ స్టార్ట్ అవుతుంది. జెనిసా క్లాస్ లో జాయిన్ అవుతుందండి. జెనిసా ఇస్ జాయిన్. Jenisa is joined. Jenisa has joined. And I'll continue. Thank you, Auntie. Yes, Jenisa. Let's continue. So basically, we have seen that in both Henry's law and Raoult's law, the partial pressure is proportional to concentration of the solute, and this is one of the problems in which we can calculate the vapor pressure over the solution based on the vapor pressures of individual components that are present in the solution. Likewise, we have seen how to calculate the number of moles of each of the components that are present in the vapor phase based on the knowledge from the values of vapor pressure of component A and component B. Moving forward, let us see in detail. Yes. Janissa, can you please read this, Amma? This is that is in bold. Raoult's law.
For any solution, the partial pressure of each volatile component in the solution is directly proportional to its mole fraction.
Absolutely. Yeah. So the P, small p, partial vapor pressure is proportional to its mole fraction. That is Raoult's law. And then this is vapor pressure, and this is mole fraction of the solvent. As I told you, when you increase the mole fraction, you see a linear increase in the vapor pressure, and this is the vapor pressure of the pure solvent, and it always passes through origin. And P1 is proportional to X1. The partial pressure of component 1 in solution is proportional to mole fraction of component 1, where P1 naught is the partial pressure of the pure component. That is proportionality constant. The proportionality constant is equal to the vapor pressure of pure solvent P1 naught. A plot between vapor pressure and mole fraction of the solvent is linear. Linear means when you increase the mole fraction, the vapor pressure also increases. That is what is called linearity. Emma, this is a typical equation of the form y is equal to mx with the slope is equal to 0. Here we do not have a y-intercept. It's not like this. It's going through the origin. Okay, ma? Such equations, such straight lines are always represented by y is equal to mx, where m is the slope. Okay. Y varies linearly with x, and the slope here is given by this y2 m is equal to y2 minus y1 by x2 minus x1. That is how we calculate the slope from the plot. Okay. We have here again ideal solutions and non-ideal solutions. Ideal solutions are those that obey Raoult's law. As you can see here, the solutions which obey Raoult's law over entire range of concentration are called ideal solutions. So what are ideal solutions, Amma? Repeat. Can you please read this?
The solutions which obey Raoult's law over the entire range of concentration
is known as ideal solution. Ideal solutions have two other important properties. The enthalpy of mixing of the pure components to form the solution is 0 and the volume of mixing is 0. Okay. Then moving forward, non-ideal solutions. When a solution does not obey Raoult's law over the entire temperature over the entire range of concentration, it is non-ideal solution. The vapor pressure of solution is either higher or lower than the value that is predicted by Raoult's law. It is if it is higher, if the vapor pressure is higher than the predicted value, that particular solution is called as the solution that has positive deviation from the Raoult's law. If the vapor pressure of the solution is lower than the predicted value, then it is called as negative deviation from Raoult's law. And you can see this is the positive deviation from Raoult's law because the vapor pressure of the solution is higher than the predicted value. Emma, this is negative deviation from Raoult's law because the vapor pressure of the solution is lower than the predicted value. This is the change of vapor pressure of component P1 as a function of mole fraction of component X1. Likewise, when component 2 is increasing this way or if it is decreasing, then you observe a decrease in vapor pressure of component 2. This is P2. And okay, neither the vapor pressure of P1 nor the vapor pressure of P2 are agreeing with the predicted values. They are deviating from the predicted values, the green lines, as per the Raoult's law. That is why the vapor pressure of the solution is higher than the, you see, the vapor pressure of two component system as a function of component A that shows positive deviation from Raoult's law, a solution that shows a negative deviation from Raoult's law. This is the solution that shows negative deviation, and this is the solution that shows positive deviation. For an ideal solution, this should be the trend. We have seen this should be the trend. When you increase the mole fraction, the partial pressure increases. When you decrease the mole fraction, the partial pressure decreases, and the total vapor pressure of the solution either decreases or increases depending on the vapor pressures of relative amounts of component A and component B that are present in the solution. Yes. Now let us see. Janisa, you are preparing for your exam, Mama. Do you face any problem with any of the study material that you are reading? In such cases, you can always share with me. Huh? I'm not able to follow this particular part in this chapter. If you say, bring me the text, show me the page number, then I can clarify. That is also possible. It's not like I teach systematically each day the content that is present in each of your chapters. You can also say that today I have read this. I have a problem in this and I could not understand this problem like that. So that way is also possible. I expect you to join in classes from tomorrow also, Janisa, I hope. Try to somehow get the permission, or if you are in your hostel room, try to connect to me through phone or whatever device you have. Hmm? Because we should continue every day, some kind of practice, some kind of revision is necessary. Emma, so I expect tomorrow that we'll continue our lecture session. Raoult's law. Then, yeah, vapor pressure of each volatile component in solution is directly proportional to its mole fraction. We have seen all these things: negative deviation of Raoult's law, positive deviation of Raoult's law. And azeotropics is another important concept, Amma. Azeotropic liquids, azeotropic systems. They are also called as constant boiling liquids, water, ethanol, and there are some specific combinations of azeotropes. Can you please read this particular paragraph for me, Janissa? Some liquids.
Some liquids on mixing from azeotropes, which are binary mixtures, have the same composition in liquid and vapor phase and boil at constant temperature. In such cases, it is not possible to separate the components by fractional distillation. There are two types of azeotropes called minimum boiling azeotropes and maximum boiling azeotropes. The solution which show large positive deviation from Raoult's law form minimum boiling azeotrope with specific composition.
Yes. So azeotropes are constant boiling liquids. And we should have some examples of azeotropic mixtures also. Like maximum, here we have two kinds of azeotropes. You can see minimum boiling azeotrope and maximum boiling azeotrope. Let us see, for example, yeah, ethanol water. You see, ethanol water is a beautiful example of azeotropic mixture. At one point of time, uh, which are binary mixtures having same composition in liquid and in vapor phase. Azeotropic composition, and they boil at constant temperature. One example is ethanol water. Uh, there should be some, azeotropic composition also. Azeotropic composition of ethanol water. Likewise, azeotropic composition of, here there is another example, nitric acid water. This is given here. 68% nitric acid in 32% water by mass with a boiling point of 393.5 Kelvin. Yeah, here. Approximately 95% by volume of ethanol. Okay, ma? Approximately 95% of ethanol and the rest of 5% will be water. That is the typical azeotropic composition of ethanol and water. Likewise, the azeotropic composition for nitric acid and water is 68:32. Huh? You should not forget this particular azeotropic composition. So these are the systems that have same composition in the liquid and vapor phase, and they boil with constant boiling point, and they are constant boiling point liquids. And typical examples of azeotropes include water and ethanol, and nitric acid and water. Water and ethanol, the azeotropic composition is 95% ethanol and 5% water by volume. Whereas in nitric acid water system, this is 68% nitric acid and 32% water by mass. Okay, ma. This is very important, and you can expect one more question from this. Okay, then the vapor pressure of pure liquids A and B are 450 and 700 millimeters of Hg respectively at a particular temperature. Find out the composition of the liquid mixture if total vapor pressure is 600 millimeters of Hg. Also find out the composition in the vapor phase. This problem is similar to the problem that we have discussed above. What we have to find out is we have the P1 and P2. What we have to find is the composition of liquid mixture if the P total is like this. Composition in the liquid phase and vapor phase. Composition, by composition, it means mole fraction x1, x2, y1, y2. Emma, this has to be found. Yeah, this is another interesting problem. Moving forward, we'll come back to this. Let us move forward quickly to the colligative properties. We discussed that the colligative properties are those that depend on the number of solute particles, but not on the nature of the solute particles. They only depend upon the number of solute particles. Okay. Can you please read what is present in the bold here, Janissa?
All these properties depend on the number of solute
That's all.
particles.
Yeah, excuse me. Yeah, all these properties are dependent on the number of solute particles and not on the nature of the solute particles. Please continue.
Irrespective of their nature relative to the total number of particles present in the solution.
Yes.
Such properties are called colligative properties.
Yeah. You will be asked to define what are colligative properties and explain. Okay, then you have to say that the properties that depend on the number of solute particles that are present in the system, irrespective of the nature of the species, are called colligative properties. And the typical colligative properties include elevation in boiling point, depression in freezing point, and osmotic pressure. Janissa, is it okay, ma? Now, let us see. We have learned in section 143 that the vapor pressure of a solvent in solution is less than that of the pure solvent. Okay. This is what is called relative lowering of vapor pressure. Emma, relative lowering of vapor pressure. This is the very, very first and fundamental colligative property. Okay. We have learned that the vapor pressure of the solvent in a solution is less than that of the pure solvent. Okay. Vapor pressure of a solvent in solution is less than that of pure solvent. Raoult established that the lowering of vapor pressure, how much the vapor pressure is lowered, depends only on the concentration of solute particles. A relative lowering of vapor pressure is proportional to mole fraction of solute. You see, you will get a beautiful equation like this. Okay, ma? This is what is called Raoult's law. X2 is mole fraction of solute. P1 naught minus P1 by P naught. P1 naught is relative lowering of vapor pressure. P1 naught is the pure vapor pressure of solvent. P1 is the vapor pressure of solvent in the solution. X2 is the mole fraction of solute. The relative lowering of vapor pressure is proportional to the concentration of solute. This is the first colligative property. Okay, ma? Based on this equation, let us try to calculate some important parameter, what is called molecular weight of solute. This is a very important problem. It will be asked for 2 marks or even 3 marks. Okay, ma? You will be asked the question, what are colligative properties? Discuss them in detail, or you will be given a problem like this. Okay. And then you will be asked to calculate the molecular weight of solute. See this equation beautifully. P1 naught minus P1 by P1 naught is equal to X2. I told you X2 is mole fraction of solute. Mole fraction of solute is again number of moles of solute divided by a mole fraction of solute means X2 is equal to N2 by N1 plus N2. And in most of the cases, it so happens that N2 is so small that it can be neglected in the denominator, and you will end up with N2 by N1. See, this is the mole fraction of solute, Amma. But what I mean to say is N2 can be neglected relative to N1. Okay. When the solute, we are dealing with dilute solution. In most of the colligative properties, or even in solutions, basically, we deal with dilute solutions. Okay, ma. In dilute solutions, the amount of solute is very, very small compared to the number of solvent particles. So N2 can be neglected in comparison with N1. So X2 turns out to be N2 by N1. Our life is made simple. Okay, what is N2? Number of moles of solute. Number of moles of solute is weight by molecular weight. W2 by M2. What is N1? N1 again, weight of N1 divided by molecular weight. So W1 by N2. W2 by M2 is equal to, when N1, uh, when we write N1 as a N1 as W1 by M1. What will happen is M1 will come to numerator, W1 will go to denominator. This is the equation you should never forget. This is the equation that is used for the calculation of molecular weight of solute. This is the equation in which Raoult's law can be expressed in terms of relative lowering of vapor pressure. The relative lowering of vapor pressure, P01 minus P1 divided by P01 is equal to X2. P01 minus P1 divided by P01 is equal to X2. Like, a parrot, you need to practice and put this equation on your notebook and solve the problems based on this equation. Emma, when I deal with one unit, you should be able to follow the same trend for unit 2, unit 3, unit 4. Because, I can rush and complete the whole unit 1 in 1 hour. Why I take slowly? Because you should not get confused. At least something, it should be absorbed by you. The pattern, if you understand, you will apply the same strategy for unit 2, unit 3, unit 4, unit 5, and you will become an expert. First thing is, you should solve all the example problems that are present in each unit. That is the key for obtaining high marks. You should know the important questions. What are the questions that are asked? Okay, the relative lowering of vapor pressure. Let us solve a problem on this because we are running short of time. Okay, so P1 naught minus P1 divided by P naught P1 naught is equal to X2. X2 can be expressed in terms of weight by molecular weight of solute divided by weight by molecular weight of solvent. So W2 by M2 into M1 by W1, and from this we can calculate either the molecular weight of solute or molecular weight of solvent, or some other parameters can be easily calculated. Let us solve one problem based on this. The vapor pressure of pure benzene at a certain temperature is 0.85 bar. Again, bar is the unit of pressure. This is the vapor pressure of pure solvent benzene. Okay, a non-volatile, non-electrolyte solid weighing 0.5 grams, for example, sugar, like glucose, was added to 39 grams of benzene, and the molecular weight of benzene is given. Vapor pressure of the solution then is 0.845. What is the molar mass of the solid? So what we have to do is, we have to find the molecular weight of solute, the added component. Emma, we know W1, we know M1, we know W2. We need to calculate M2, molecular weight of solute. So P01 is the vapor pressure of pure solvent benzene. What is the vapor pressure of pure solvent benzene? 0.850. What is the vapor pressure of solution? 0.840. Write down the equation. P01 minus P1. P01 P01 minus P1 divided by P01 is equal to is equal to W2 by M2 into M1 by W1, and what we want is M2. Emma, substitute P0 1.85 minus 0.845 divided by 0.85 is equal to then wait W2. What is W2? This is weight of the solute. And the weight of the solute is 0.5 grams divided by the molecular weight of solute M2. It is not known that we have to find. Multiplied by molecular weight of solvent. The molecular weight of solvent here is 78 gram per mole. Likewise, the weight of solvent is 39. Substituting the molecular weight of solvent for M1, substituting the weight of solvent benzene as 39, we can end up with M2. M2 is equal to 170 gram per mole. Is it clear, Amma? Can you calculate such problems, Yunisa? Easily. No problem. Yeah. Now, let us see. What is happening is relative lowering of vapor pressure of solvent when a solute is added. P01 minus P1 divided by P01 is equal to X2. It should be remembered in your mind. Then, elevation in boiling point. Elevation means increase. Okay. The increase in boiling point. Simply, you can see from here, the boiling point, this is the boiling point temperature. This is the vapor pressure. When we add a solute, the boiling point is increasing from T1 naught to TB. This is what is called the elevation in boiling point. Okay. When you see a plot of vapor pressure versus temperature in the solution, the boiling point is higher than that of solvent. This is what is called elevation of boiling point by the addition of solute, and delta TB is equal to delta TB. This is delta TB is equal to TB boiling temperature of solution minus boiling temperature of solvent. This is called delta TB is called elevation of boiling point, and this is again proportional to molality. Okay, ma? Can you please read this title, Janissa?
Boiling point elevation constant or molar elevation constant.
Yeah. Yes, that is good. But this caption, figure caption.
Oh, that one. Okay. The vapor pressure curve for solution lies below the curve for pure water. The diagram shows that delta TB denotes the elevation of boiling point of a solvent in solution.
Absolutely. So we are dealing with the elevation in boiling point of solvent by the addition of a solute. Okay, delta TB corresponds to how much the boiling point of the solution is, how much the boiling point of the solvent has increased when we form the solution. This is the typical plot. Okay, when you want to explain the colligative properties, you should remember these plots. Okay, ma, the temperature. At atmospheric pressure, the temperature corresponds to atmospheric pressure is called the boiling point temperature. Experiments have shown that for dilute solutions, the elevation of boiling point is directly proportional to molar concentration of the solute. This is very important. Emma, can you please read once again? From here.
For dilute solutions, the elevation of boiling point is directly proportional to the molar concentration of the
That's all.
solute in solvent.
That's all. Delta TB is proportional to M. Like Raoult's law, the dependence of elevation in boiling point of the solvent is proportional to molality, and molality is number of moles of solute present in 1000 grams of solvent. Emma, okay. Yes. Can you please read from here? Here.
Here, molality is the number of moles of solute dissolved in 1 kg of solvent, and constant proportionality Kb is called boiling point elevation constant or molar elevation constant, helioscopic constant. The unit of Kb is kg mole inverse. Values of Kb for some common solvents are given in the table.
Absolutely. Please stop. So, molar elevation constant. Kb can be called as molar elevation constant, like Kh, Henry constant, like P01, pure vapor pressure of pure solvent. Here simply it is represented as Kb. This is what is called a molar elevation constant, and it is a constant, and its unit is basically it should contain temperature and concentration, delta TB divided by M. So Kh, okay, Kelvin, kilogram per mole. That is the unit. Emma, because Kb, helioscopic constant, is equal to delta TB. Hi, 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 baboy, hi, baboy, hi, baboy. All kinds of problems will crop up when I want to complete something. There is again a charge problem. Let us try to overcome this problem. I don't know how. Yes. I'm sorry, Janissa. Yeah. Now I could connect it to the power. Yeah. See, we have delta TB is proportional to M. M is molality. Delta TB is the elevation in boiling point. Here all around there are some students, they're studying, so I don't want to raise my voice, they get disturbed. Yeah. Hope I'm clear. Yes. You see, Janissa, here uh, we have this delta TB is equal to KB into M, and KB is molar elevation constant or abelioscopic constant, and the unit of KB is Kelvin kilogram per mole. Values of KB for some common solvents are given in table that will come back. If W2 grams of solute of molar mass M2 is dissolved in W1 grams of solvent, then molality of the solution is given by moles of solute per 1000 grams of solvent. This is the molality. W2 by M2 divided by W1 by 1000 is equal to W2 by M2 into 1000 by M1. Basically, we'll be knowing W2, we'll be knowing W1, we'll be asked to calculate M2. This is the molecular weight of solute, like the previous problem. Once we have the values of partial pressures, uh, we know the amount of solute. We have to calculate the uh, molecular weight of solute. This is one problem that is frequently asked. You can see here. In delta TB is equal to KBM, let us substitute the value of here we have delta TB is equal to, okay, KB, abelioscopic constant into molality. Abelioscopic constant into molality is easily, how can you remember? I'll tell you. Delta TB is equal to KB into W2 by M2 W2 by M2 into 1000 by W1. Okay. So this weight of solvent will be given, weight of solute also will be given, abelioscopic constant also will be given, elevation in boiling point will also be given, and you will be asked to calculate molecular weight of solute. Emma, let us see one problem here. Can you please read this problem, Janissa?
18 grams of glucose is dissolved in 1 kg of water in a saucepan.
Excuse me.
At
Wait.
what temperature?
One second, Janissa, please wait. This is W2. Emma, always solute should be expressed as 2. Okay. Solvent should be expressed as W1. So W1 is 1000 grams and W2 is 18 grams. Okay, then the temperature.
At what temperature will water boil at 1.013 bar? Kb for water is 0.52 kg mole inverse.
Okay. KB is given. KB is 0.52 Kelvin kilogram per mole. Okay, ma. Abelioscopic constant is given. We know the amount of glucose, that is 18 grams. From 18 grams, you can calculate the number of moles. Weight by molecular weight is number of moles. Okay, we have the number of moles of solute, number of moles of solvent is also present, and molality is grams of glucose. Molality of glucose solution is moles of solute per 1,000 grams of solvent. 0.1 moles per kg. This is the molarity. For water, change in boiling point. Okay, that is delta TB. TB is boiling point. Delta TB is change in boiling point. What is the formula for delta TB? Ebuloscopic constant Kb multiplied by molality of the solution. Ebuloscopic constant, what is the value of ebuloscopic constant? 0.52.